Hi guys, welcome back to Learn Electronics Repair, and it's time to reveal the solutions to the 3 problems I gave you in the Learn Electronics Repair Christmas quiz. Yeah. Just before I do that, I'd like to say thanks guys to you, because the response I got to this quiz was amazing. I was really surprised to find how many of you wanted to have a go at these questions, whether one or more or all of them. And some of you guys got them right, some of them got some of them right, and Detlef's just wandering around behind me. Oh, there you see, he's still around. So Detlef also got the one with the diodes right, and the other 2 he actually knew. And that's because, in part, the other 2 we actually did on the live stream on Sunday gone before I published the quiz. And some people there were just amazed at the answers. So thank you very much. I really appreciate the fact so many of you wanted to get involved, and now I'm sure you want to know what the answers are. So here is our resistor network made up of 1K resistors. So we have 8 1K resistors here. All the resistors are the same value, 1000 ohms each. And the sharp-eyed ones of you might notice this is actually a different one than the one I showed yesterday. That's because for the life of me, I can't figure out where it's gone. After spending 10 minutes looking for it, I just decided to make another one. So there we go. So there's our resistors. And the question, of course, was what is the resistance from A to B? Well, the easy way to work this one out is to build one and measure it. I know at least a few of you actually did do that, yes, and you came up with an answer. But before we do that, let's just have a look at this in theory and see if we can work it out, okay? So, as I mentioned in the first video, we have 3 pairs of resistors, and each pair are resistors in series. So we have like so. I must learn to draw better today. There's my 3 pairs of resistors, and each one of these is 1K. And then we put all of these pairs in parallel. And at this point, it actually is not too difficult to work out the resistance. The complication came when I put the other resistors from here to here and here to here. That's when it got complicated. So just for a moment, let's ignore those other 2 resistors and work out what the resistance is here. If you know the formula for resistors in series, it's very simple. You just add them together. So 1 plus 1 is 2. So here we have 2K. Again, 1 plus 1 is 2K and 2K. So what we actually have, the equivalent of, is 3 2K resistors. I made a video about the formula to work out resistors in parallel, but this one is not quite simple, because if you have 2 resistors of the same value in parallel, the answer is half. So if we had 2K and 2K in parallel, the resistance would be 1K. If you had 4 pairs in parallel, it would be a quarter, 500 ohms. We have 3. So the answer to this resistance from A to B is 2000 divided by 3. And that is 666. Okay, 0.66. But it's 666. You see, the devil is in the detail, yeah? So that is the resistance we have there. Now, before we go to our network, I want to draw something else, okay, using these 6 resistors, and that will give you a good idea of the reason for the answer to this one. So let's do this again. Let's have 3 resistors. Each one 1K, okay, and then again 3 resistors, 1K, 1K, 1K. Now we'll connect all these ends together, okay, And we'll connect all these ends together. Like so. And like so. And we'll connect from here to here. Okay. It may look different, but all we've really done is just connected a wire directly across there. Okay. That's the same as that. The reason I've drawn it this way, it's a little bit easier to understand. So, what's the resistance from A to B? Well, we have 3 1K resistors in parallel. So the total resistance is a third of 1K, which is 333. Yeah, 1000 divided by 3. And the same here. Can you see where this is going? 333. And the total resistance is 666. I told you the devil was in the detail. So what we've just proven is whether this is open circuit or whether it's shorted together, the resistance doesn't change. So infinite resistance from here to here and infinite from here to here has no effect. 0 from here to here, 0 from here to here gives exactly the same reading. So from that, I think you can project the fact that any resistance here and here won't affect the reading. It could be anything from 0 ohms to infinite ohms. Yeah, and it won't affect the reading. And we can prove that by measuring this one. So this should read 666. Now, these are 5% tolerance resistors, so they're not going to be exact, so the reading won't be exact, but it should be somewhere near to that. So let's measure it. Ohms range, here to here, 654. And I say these resistors are not exact. 654. Okay. And we'll do what we did here. We'll make this circuit. So we're going to short out these 2 resistors. Okay. We've shorted them both out. Okay. What's the reading? Well, this tells us 666 or close to it with the tolerance of our resistors. 653. Let's just short out one of them. $653. So shorting either one or the other has no effect. Okay, we'll short in both. Let's get rid of these resistors. We can get rid of one of them. What do we have now? 653. Get rid of the other one. $653. Okay, so you can see that this theory we just looked at, yeah, we've done it practically and we've proved that is the case. The question is now, I'm sure you want to know, is why does this happen? Well, Detlef, who's round the corner, tells me that there's a law, like we have Ohm's law, called Kirchhoff's law, Det?
Kirchhoff, he was a German, of course.
Ah, Kirchhoff, who was a German, of course, and he proved mathematically why this happens. But I'm actually going to tell you in very simple terms why it happens. Thanks to a German named Kirchhoff. So, let's have a look at it. We have 3 pairs of resistors. Okay, and they're all the same value. And it doesn't matter what the value is as long as they're all the same. This only works, by the way, if these resistors are all the same. The other 2 could be any value. Same as each other, different to each other, any value from 0 to infinity. Okay. Let's look at our circuit again without the other 2. what's the voltage here? Ask yourself, what is the voltage here? Well, you're going to say, I can't tell you, Rich, because I need to know the voltage across the resistors. So let's stick some voltage across the resistors. Let's put 0 here and let's put 10 here. What's the voltage here? Well, if you understand how a potential divider works, the voltage here depends on the proportion of these two resistors. Not the values, but the proportion. If they're both the same, then the voltage here is half the voltage there, 5 volts. Okay, and that would apply if these were both 10k resistors or 100k or 100 ohm. It would be 5 volts here. And if we change the voltage here, say to 6 volts, the voltage here would be 3 volts. So it will always be half of the applied voltage. And when we connect our multimeter to measure the resistance, our meter applies a voltage across the resistors. That's how it measures the resistance. So whatever voltage we put here, half of it will appear there. And the same will apply here. That'll be half of it. And the same will apply here. It'll be half of it. So the voltage at all these 3 points, we'll go back to the 10 volt example, will be the same. It will all be 5 volts. So what happens if I put a resistor here now, or even a short circuit here now? What current flows between here and here? Well, they've got the same voltage on both ends, so no current flows from here to here, 0. If no current flows through the resistor, your meter can't measure any resistance. Yeah. No current flowing through it. Therefore, as far as you're concerned, it doesn't exist. It's not there. If no current can flow through it, well, it's not there. Okay? That's why this will always read 666. Yeah, it was a beast of a question. Well done to those of you who got this right, and for those of you who got it wrong, and even the ones who did get it right, because you might have found somewhere online that told you this. Now I hope you understand why. Okay, so that's the solution to question 1. And so on to challenge 2, this one. The challenge with this is, what's the voltage in the capacitor? So we have 4 LEDs wired in series, all in the same polarity, same direction. Then we have a capacitor, and from the other end the capacitor goes back to the start of the string. Now, a number of you got this one right. Well done, guys. But there was some debate as to the reason why. I'm going to explain why it happens in my opinion, and I'll also explain the other opinion. Then we'll test it, yeah, to see which is actually correct. But the question is first, what's the voltage in the capacitor? Well, there's no exact answer to this because it will vary to some extent. And one of the main factors that it will cause the variance is how long you've left this thing sitting around. I've had this sitting around for about 24 hours, just lying around on the desk. It's been here all night. So it's been here for quite a while. So let's have a look. What is the voltage across the capacitor? I have the meter on volts range. Let's have a look. Well, I think you saw there we got 3.1 volts and now it's going down. And it will keep on going down and gradually get down towards 0, okay? Yeah, 0. So the capacitor is discharged. First question is, I guess you want to know, is where did the voltage come from? But your other one might be, why did the capacitor discharge? And I measured the voltage. Well, I'll answer number 2 first, and then we'll look at number 1. Yeah. So the reason the capacitor discharged is when I connect my multimeter to the capacitor, my multimeter has a internal resistance, okay, an input resistance, and that is 10 mega ohms between these probes. So when I attach my meter, it's the same as attaching a 10 meg resistor across the capacitor. The capacitor is 100 nanofarad, it's not a large value one, so that will cause the capacitor to discharge. And I can prove this because if I now go back onto here again and measure again, you see, it's got a bit of charge back in. It was back up to about 0.15 of a volt. And if I leave this for some time, it'll go back up to about 3 volts or so. So that's the answer. 2.5 to 3.5 volts, but depends on how long you leave it before you measure it. Okay. Now, where did the voltage come from? Well, there are 2 conflicting theories on this. I'm pretty sure I know which is the correct one. So I'm going to explain in my version where the voltage comes from, and then we will test the other version. Okay. So this is the way this circuit works. We have four LEDs in series, okay? It doesn't matter the polarity as long as they're all the same. All that will happen if you put the LEDs the other way around is the voltage and the capacitor will be the opposite polarity, but it will still give you the voltage and the capacitor. There's your capacitor, okay? And then this is your piece of wire. Now, an LED is a diode. It only passes current in one direction. So we can draw an equivalent circuit of this and just put a diode, okay, or some of them in series. Okay. A piece of wire, any piece of wire or any PCB track, regardless of whether it's connected in a coil or not connected in a coil, a piece of wire is an inductor. Okay, any connection is effectively an inductor. It has some inductance. So our piece of wire effectively is an inductor. Okay, and connected across the output of this circuit is a capacitor. So any voltage induced into this inductor will be rectified by the diodes and will charge the capacitor. Where does the voltage come on in the inductor? Well, it's out of thin air, because the thin air that we all sit in is completely filled with radiation. Especially these days, Wi-Fi, mobile phones, radio stations, TV stations, even the mains wiring is radiating an electric field at 50 hertz. And this inductor will pick up that radiation. The diode or diodes will rectify it and the capacitor will charge. And when we connect our 10 meg resistor across here, the voltage discharges. So I use 100 nanofarad. The value isn't critical again. You need a capacitor that has an extremely low or no leakage current, because the charging current for this is very, very low. If you replace this with a multi-turn coil, it would be faster because it has more inductance. So that's where the voltage comes from. You guys might have heard, especially some of the older ones, of a crystal radio set. So a crystal radio set, you had an antenna connected to a coil, and effectively from here you had a crystal, which basically is a diode. You can use a germanium diode, and here you had an earphone, very high resistance or impedance earphone, and you had a tuning circuit in this. Okay, the tuning circuit would allow you to listen to radio stations, and you can actually hear the radio stations with no battery, no power. Okay, that might not be the exact circuit, but you get the idea. Crystal radio. If you haven't heard of that, go and look it up. It's an interesting topic. We can build one, yeah. So if you know about the crystal radio, you've probably never really thought it was a strange thing that you have sound coming out of the speaker, because there must be voltage across it. So really this is just the same circuit. I'm just charging a capacitor. So that's how it works, but there's another theory. And the theory goes that these light emitting diodes are also light sensitive diodes or photovoltaic cells. And by shining a light on the LED or daylight, you generate a voltage, like a solar panel, effectively. Low power, but it charges the capacitor. Now, we tried this on the live stream, the electronics channel, on Sunday when we first demonstrated this. And we tried shining a bright light on the LED while simultaneously measuring the voltage, and we couldn't see it made any difference. So I'm going to prove this. I'm going to put some black insulation tape around these. We're going to discharge the capacitor afterwards, and I'll put this on one side so no light can get on it. And let's see if the capacitor charges back up again. Okay, so I'm now putting the black tape on. I've completely covered over these LEDs. I hope you're satisfied. You can see that no light can get in there anywhere. Okay, let's measure the voltage, which of course will discharge the capacitor. So volts, what do we have? Well, just over a volt, and it's now gone to 0. Yeah, I lost the contact, but okay, so we've discharged the capacitor. So I'll put this on one side and we'll have a look at the solution to problem 3. And here is challenge number 3. So this is the circuit that I showed you with 2 switches and 2 light bulbs and a transformer. But as I explained, there are 3 more components that complete this circuit. They're hidden around the other side of the cardboard. So the challenge was to add 3 components to this circuit to make it behave like this. We press this switch and this bulb lights. We press this switch and this bulb lights. And if we press both, they both light. So that's the way it works. How can it work like that? Yeah, because it doesn't seem logical, does it really? Well, actually, it's very logical. So the first thing we need to take into consideration, because I'm sure we know this, the transformer is providing AC. So coming in here is AC. Okay, it's an AC signal. Because it's AC, on the positive half cycle, the current will travel in one direction, let's say that way, and in the negative half cycle, it will travel in the other direction. Okay? So that's how the current is actually flowing. So what we can do is make this circuit behave in different ways depending on the polarity of the signal. And we do that by using diodes. Because, as I hope you all know, a diode passes current in one direction and blocks it in the other. So, bearing that in mind, if we want this bulb to light when we press this switch, we can do that by adding a diode. Okay, so I'm going to put a diode here, from here, and connect it to here. Okay, so when I press this switch, the negative half cycle causes the current to flow that way. It flows through the light bulb, through the diode into here. Will any current go down through that bulb? No, because this switch is off. Okay, so the only circuit is this. That's why this bulb lights when you press this switch. How do we get the other one to light? Well, all we've got to do is to make a circuit path using the other half cycle. So, to make the circuit that passes current in that direction, we need to add some diodes. This switch is open, but we need to pass current when this one is closed. So we can fit a diode here, this way. Okay. Will that affect the negative circuit? No, because the diode is reverse biased. When that switch is closed, the current goes through the switch. In fact, when that switch is closed, the diode is shorted out anyway. Okay. But when the switch is open, your positive half cycle comes through here, through this switch, through this bulb, and now we need to get back from here to the other end of the winding. So we add another diode, okay? And this diode goes from here back to the other end of the transformer. So I hope you can see it now. In the positive half cycles, we have a path through the diode, through the switch, which is now closed. Okay. Back through the bulb and back to the transformer. So positive half cycles follows that route, and negative half cycles, well, the diode's blocking it, it's reverse biased. The negative half cycles have to go the other route, which is through this bulb, through this diode, and back to there. Okay. And when they switch both on, well, both lights light at once. But in actual fact, really, they're not both lit at once. They just look like they both lit at once. That's because this one is only passing the negative half cycles. Okay. So the positive half cycle is being blocked. And this one is only passing the positive half cycle, which is in between. So if we draw it here, this is passing that. Okay, so actual fact, the lamps are both flashing on and off 50 times a second. But because these are filament lamps, you don't see that. Okay, so that's how the challenge works. Okay, a few of you got that one right. Also, now Detlef actually built this circuit in a different way, using 3 diodes, but it still did the same thing. It still gave a circuit through one switch in a bulb in one direction and a circuit through the other one in another direction. He used some emulation software, Detlef?
Yep.
Yep. He used one of these online circuits. Pardon?
Fortstat.
Yeah, so it's in your WhatsApp, you can show the people.
Okay, Fortstat. That's what he used. Okay, so he used an emulator. I actually saw this challenge myself online and I worked it out myself, and this is the combination I came to. So I just did it on paper, basically. So well done to you guys who got that one right. One more thing to do then, and that's to see if our capacitor is still charging up with the LEDs blocked out. And here it is. Do we have any charge in our capacitor? I'm going to be completely honest now, guys. I've not tried it. Okay. We did a bit of experiment with a bright light and it didn't see any effects, but I have not tried this. So this is where Richie can get proven completely wrong. Either it's a photovoltaic action caused by the light, or it's a generation of electricity by the radio frequencies that are in the air. Okay? What do you think? What do you think? Well, I'm going to find out right now. Yeah? Does the capacitor still charge? Not as much. The answer is yes, but not as much. I didn't leave it for very long, but from the result of that, it would seem that the action is neither totally RF generated, nor is it totally light generated by the LEDs. So I think we can actually say that we're both right. I think it looks like it's actually a combination of the two. Well, how about that? Who expected that? I certainly didn't. Okay, thanks for watching. Thanks for getting involved. Thanks for all your comments on the previous video. I'm sure there'll be plenty more on this video. And let me know if you'd like to do a similar thing again sometime. Merry Christmas, guys, from LER Electronics Repair. Ciao for now.